Hey everyone, today we're going to take a look at how to build a deterministic time API for playable content in the browser. My name is Jacques and I work for a company called Milk Video. We help salespeople and marketers turn webinars, sales demos, and other long-form content into short, shareable clips. Here you can see how our platform works. And on our platform, users can also add designs to their clips, kind of like Canva. And they can add animated captions, all from within their browser. This means that we needed a consistent way to sync up all of the different elements on the canvas when users previewed the clip in the browser, as well as for when we rendered their project to MP4 files, because we also used the browser for rendering. So first, let's take a look at how we used to do this. So here's a quick diagram showing how our state used to be set up. We had two pieces of core state. The one was just a Boolean, which represented whether or not the project was playing. And the other was a timestamp, representing when the project started playing. And some of the components, such as the timecode and captions component, would run a loop to calculate the current time based on when playback started and whether the project is playing. And then in that loop, it would take the current time, calculate some other piece of state, such as which word was active, and react accordingly. And for video elements, we would just play or pause them, depending on whether the isPlaying Boolean was true or false. And finally, for elements like the export button that displayed the project's total time, we would use the project duration property that was stored in the project state. And this property was updated whenever we inserted or removed items. So whenever we inserted an item, for example, in that insert item function, we would also recalculate whatever the longest item was on the canvas and then set the project's duration to that value. Same for when we removed items. So we had a completely disconnected mix of ways of handling our state. We had some state that was kind of reliably and reactively derived from the core playback state, such as the captions or the timecode. We had some imperative calls based on changes to that state, such as the video element. And in the case of the project duration, we had what I refer to as synced state, where you have a function that makes the main update, so for example adding an item, but then also has a function call within that to update some sort of dependent state in a very sort of imperative, direct way. But this model started to become a problem when we started building a new feature called highlight reels. And this feature would let users combine multiple clips into a single video. So here you can see I have my single scene video, but I actually want to display multiple clips. So let me quickly show you how this works. So here you can see I have my project and I have a single clip with a specific title and design, but I actually want to display another clip as well. So I'm going to add another scene and drag in my other clip and change the title. So the first clip is going to play, it's going to show that design with that title, and then later on, once that clip's finished playing, it's going to move on to the next one. So basically just like multiple chapters or multiple projects almost that are strung together. And our first attempt at this implementation was to keep going with the synced state route. So we had a bunch of different scenes, and each item on the canvas would belong to a specific scene. And the length of the scene was stored as its own value, meaning that whenever we added or removed an item from a scene, we had to recalculate the scene's duration and update it. And in simple cases, that worked just fine. But what if we added another action to, say, paste a clip? Well, that would also probably change the scene's duration, right? But because we didn't have that recalculation in that paste action, we wouldn't actually update the scene duration. So there could be inconsistencies in the state. And not only did we store each scene's duration in its own state, we also stored the active scene in its own state. So when the user pressed play, we had to compute what the active scene was, meaning which items should display on the canvas. But what if playback was paused and someone deleted a scene, for example? Well, then we'd have to add logic there too to also recalculate the active scene. Or what if someone deleted an item from a scene, which changed its duration, which based on the current play time, then changed the active scene? There are just too many events and orders of events that could affect these computed synced state values that it was impossible to keep up. And this implementation is just asking for bugs to appear as you change or add things. And as we worked on the implementation, that's exactly what happened. It became unmanageable. The problem with synced state, the fundamental problem, is that you have to consider every single action that might affect your state and make sure you compute and update the state correctly. So we tried a different approach. Our goal was to build a single source of truth for time and for any value, UI, or side effect that could possibly be derived from that single time state. And it had to work while playing back in real time and with any other kind of arbitrary change in time, such as when someone seeks or scrubs. So this is how we set up our new time API. We had this global context provider, or rather the context provider wrapped any components that needed access to time. And there were two core pieces of state. The one was a timestamp for when playback was started, or it would be null if it's not playing, so if it's paused or if it's stopped. And then the second value would be the play offset, meaning the last time code that the project was seeked to. And based on that, we can derive whatever the current time should be for the project. And along with this provider, we created a use playback hook, which lets any component subscribe to the current time, whether or not the project is playing back, and a few other helpful functions, well, necessary functions, like playing, pausing, seeking, and so on. And this was really great. This gave us a very, very reliable interface for reacting to the current time. Because the idea was here to let React do the hard work for us because, well, React is very, very good at rerunning functions whenever dependent state changes. That's kind of what it does, right? But it was almost too good because we soon ran into performance issues. So because of the way our API was set up, any component that used this use playback hook would receive the current time value, but the problem was that that current time value changed every single frame. So any component that used that state, and that was pretty much every component on the canvas, would re-render every single frame. And in React, re-rendering is slow because you have to rerun the entire render function, not just like the small bit of the UI that depends on the time. Anything else within that component's got to re-render as well. That would cause most of that component's children to re-render, and then React has to also do a diff to figure out if anything needs to actually change in the DOM. The point is, it's not advisable to rely on React for rendering things at 60 frames a second. But needing to re-render the component every frame isn't really necessary, because even though our current time might change every single frame, in our captions example, the index of our current word wouldn't. That would only change, once every 300 milliseconds or so, because words are generally longer than one frame, right? And previously, this wasn't an issue, because we were just running a loop in every component that needed the time, and we ran it outside of the React render loop. And then whenever any sort of derived state, so the active word, for example, would change, then we would call a set state to re-render our component. So it was pretty efficient. So then we thought, instead of having all these different loops scattered around our code base, like independently figuring out what the current time is, what if we had one central loop that calculated the current time, and then components could efficiently react to that and subscribe to that without them all having to re-render every single frame? And out of this came two standardized hooks. The first one we actually borrowed from the React Redux library, and we called it use time selector. So here's the idea. We have a request animation frame, which when the project is playing, runs every single frame. That calculates the current time, and that dispatches a time change event. And then any component that wants to subscribe to that current time change could do so by calling the use time selector. And then that component would then run a function every single frame or whenever time changed to determine a new resultant value. And if that value changed, it would re-render. And as you can see, the only part of this whole flow that actually involves React, i.e. the expense of computation, is the last step. And that happens a lot less often than everything else does. So the idea behind a selector is to run a cheap computation often, and then only trigger a more expensive computation whenever that cheap computation returns a new result. The expensive computation being a re-render in this case. And another thing that was very cool about the selector was that we would call the function whenever current time changed because of any reason. So either because of playback, so whenever that request animation frame loop was called while playing, or whenever the play started value changed, meaning regardless of whether the user was playing back the project, seeking, or seeking while playing, that selector would be called and any dependent UI would rerun their calculations and update. Or even if someone deleted like the scene in front of the currently active scene and the active word that should have been highlighted in that caption changed because that scene was deleted, it all just ran reliably, no matter why the current time changed. And we also had to make sure that the videos were played and paused and seeked to the right time, depending on the global time of the project. So the second hook that we created is borrowed from React, and we call it useTimeEffect. And this hook, quite simply, lets you fire side effects whenever the current time changes. So in here, we could simply seek the video element to the correct position. And it kind of works like useTimeSelector, where you can pass it a function that'll be called whenever current time changes. The only difference is it doesn't return anything because it's meant for side effects. In fact, internally, useTimeSelector is actually built using useTimeEffect. Pretty neat, right? And because this is such a foundational piece of our application, we wanted to make sure that it always worked, meaning that we probably needed some tests. At first, I thought it would be a bit of a challenge testing all of this because it involves behavior over time and request animation frame, but it ended up being surprisingly easy. So let's say we wanted to test whether playing and pausing worked. So ideally what we would do is we would test our hook the way that it's used in real life, right? Because testing your software the way someone is going to use it or the way some other code is going to use it is the best way to test it, right? So hypothetically, what we would do is we would set up a test like this that would render our usePlayback hook. It'd start playing, it'd wait a second, and then check the current time to make sure that it is set to a second. So we're testing that it started playing and that it's like moving forward the correct amount of time. Then we would pause and then maybe wait like another second, and then make sure that it actually paused after a second. So make sure that the current time is still 1 second instead of 2 seconds. Pretty simple, right? That's exactly how it would be used and how we would expect it to behave. But we don't actually want this test to run for 2 seconds. So we needed some sort of a way to run this test without real time being a factor. So because this hook is based on the actual JavaScript date, we needed a way to mock the date. So we used this library called mockDate, which works with Jest. And how this works is you render the hook, and then we set the time to 0. So if you called date.now in JavaScript, you would get 0 back. We start playing, and then we can time travel forward by a second by setting the date to 1,000. And then we make sure that it's playing, so make sure that the current time is 1,000 and that it moved forward the right amount of time. Pause, and then time travel forward another second, so set the actual time to 2 seconds, and then again make sure that it's paused. So the same test, but not involving any real time, which is pretty cool. The other thing that we were missing was the fact that our useTimeEffect and our useTimeSelector hooks depended on request animation frame while the project was playing. And we couldn't actually run that in Jest because Jest doesn't support request animation frame. So what we did was we replaced request animation frame with a set timeout and used Jest's use fake timers feature. So this turned off real time in timeouts in Jest. So let's take a look at how this actually works. So first, before each test, we enable the use of fake timers, and then we replace the real request animation frame implementation with a custom one that just calls a set timeout that resolves after 50 milliseconds. And then in our test, so here you can see we have a test that mounts the useTimeEffect hook and has some sort of test function. And we want to make sure that this test function is called whenever the time changes. So first, we set the time to 0, just like we did in our previous test. Then we start the playback, so we use our usePlayback hook here. And then we advance the time by 50 milliseconds and also trigger a frame by telling Jest to also time travel 50 milliseconds, which would trigger one call of our set timeout. And this would give us a way to frame by frame advance time so that we can test things very, very granularly. To test that our test callback was called once by our useTimeEffect for that one frame that we advanced it by. And using this time traveling principle, we could test anything that depended on our time system, including making sure videos were being seeked to the right time and that the correct caption word was being highlighted. And all of the tests could run faster than real time. Now, one tricky thing that we still had issues with was keeping our video elements synced up with the rest of the items. Because what happens is you press play and we record the play started value immediately, right? So time starts to advance. But because the HTML5 video elements on the page take a few milliseconds to start, or they could be buffering or something, or the browser could just be busy, or there could be Bluetooth delays, all manner of reasons, the video elements might actually start playing quite a bit later than our internal time is storing. So there were a few solutions that we thought of there, but the simplest solution, and the one that we're using right now, is we start playing and the time starts advancing, but then all of the video elements on the page call back to the time system periodically to tell the time system what their internal state is. So if there's any kind of drift between the two, the video element is going to tell the time state to actually seek to the correct time. So basically, the video elements start playing because of the time system starting to play, and then now and then they call back to actually update their real time and sync the time system back up with the video element. But there is a very promising proposed web standard called the Web Timing API, and we're going to be experimenting with that pretty soon. We haven't looked at it yet because it's still very early, and there is a JavaScript implementation of it, but we haven't really looked at it much. I just thought I'd flag it though in case anyone else wanted to play around with it, because it does seem like a really, really good solution to keeping video elements in sync. Now, looking towards the future, the way that we've set up this time system actually lets us do pretty interesting things. The first, and what we're currently working on, is something called frame-by-frame rendering. So the way our recording works now is we open up the canvas in a headless browser, we play it back and screen record the page. And this has actually worked really well for us in the last while, but we've had quite a lot of quality and frame rate issues just because we're dependent on the browser and the recording system always performing perfectly, because everything's got to happen in real time, right? But right now we're actually rebuilding our rendering engine to render videos frame by frame. So what this means is we're opening up the app in a headless browser, just like we would for screen recording it. But instead of screen recording it, we take a screenshot of every single frame. Now, without this deterministic time system, we wouldn't be able to just call a function on the page to advance the time frame by frame. We wouldn't be able to just arbitrarily seek to a specific time or frame in our video and be confident that everything displays correctly. Another thing we'll be adding soon is animations. Again, we can leverage the time system we've built to create interpolation-based animations, where for a given timestamp or for a given frame, we output a specific CSS value. So for example, from time 0 to time 200 milliseconds, we could interpolate an opacity value from 0 to 1, and that gives us a fade-in animation over 200 milliseconds. And what's cool about this, because again, it doesn't rely on CSS animations, it's completely stateless, this will work with our frame-by-frame rendering. So what have we learned from all this? Well, we've learned that the best way to handle time in the browser is to derive the properties of your UI elements directly from your time in a declarative way. And that the best way to structure your time system is to build a single source of truth for your time, and a standard and centralized way to derive values and run side effects from changes to that time. We've also learned that you should do this by taking advantage of the library that you're using to build your UI, be it React or Vue or Svelte or even Angular. Also, we've learned that you should be conscious about not overusing your UI libraries and leaving often running calculations outside of the expensive render cycle to more efficiently update our UI. And finally, we've learned that the most important thing to focus on is giving the user a delightful, performant, and most importantly, reliable interface to work with. So that's been our journey to creating a time system for the web. I'll post these slides on Twitter if anyone wants to reference them later, so you can find them there. And one last thing I'll mention is that we're looking for talented front-end and video engineers to join our team. We've got a lot of interesting problems to solve and would love for you to join us in solving them. If you want to have a chat with us about that, you can get in touch directly with me or with Milk Video's founder, Lenny, on Twitter. Thank you so much. I hope you've learned something along with me, or at least had some ideas. And I'll see you on Twitter.